Namaste everyone. Welcome to second BSc Physics class. Today we will start a new chapter, that is atoms. Right? Hope you have revised that electric field and charges, because it is very much needed here in all derivations. Right? Hope you have seen that, at least up to Coulomb's inverse square law. So namaste everyone. Hope you are doing well. So how is the atom structure discovered? Nowadays we know that atom is having a model like a planetary model in which the sun is at the center and all the planets are revolving around the sun, and similarly atom is also designed, and it will have a central nucleus and electrons are revolving around the nucleus. How this was discovered? Initially when a metal or a coil is heated, in the olden days when scientists were doing the experiment with the heated coil, electrons used to come out, but they didn't name it as electron, and it was named as a cathode ray. And when that beam of electrons is made to hit some photographic plate used to show the light. So that is because electrons go and hit the photographic plate, and electrons in the photographic plate absorb this energy of the moving electrons, and they emit that energy in the form of light. So energy of moving electrons were absorbed by the electrons in the material, and they get the energy, they go to the higher energy state, and they release that energy in the form of a light. It is like a barter system, right? In barter system, what do? We give something like rice or anything, and we take another one. Suppose one country is very good in, very expert in preparing clothes, different types of varieties of clothes, and if we are good in agriculture, so we will give wheat and we will purchase cloth. So like this, that is barter system, no money, right? Similarly, the kinetic energy electron, when the electron moves with very high kinetic energy, it has some velocity, it has some kinetic energy hidden within it. So it donates its kinetic energy. But electrons inside the material, that the target where we hit the electron, they don't have that energy. So they absorb that energy from the kinetic energy from the moving electron. Moving electron loses all its kinetic energy. So this electron gains that energy, and that when it gives it back in the form of light. So kinetic energy is converted in the form of electromagnetic radiation. So that photographic plate, when it receives the high kinetic energy electrons, it used to give light. So scientists used to see this phenomenon when a metal is heated. Electrons used to come out, but they didn't know that it is electron. They just thought that there should be some particles coming out of this heated coil and the cathode. So when it emitted electrons, when it falls on a photographic plate, it started emitting light. So that should be some particles within the material. That's what the conclusion made. And later on, it was found that they are the electrons. So some particles must be within the, some basic particles, building blocks must be within any material. And it was J.J. Thomson who started giving a structure for the atom. Right, and from one side, some other inventions also went on, like there should be a smallest particle, and it can be named as particle, for example. And Indian scientists named it as Kanada, right? Kanada scientist named it as a Kana. It is the smallest particle available in a material, and you know that you studied it in kinetic theory of gases in the first year, right? So that gives that there should be a small particle and called Kana, and later on it was found that there are molecules inside all these particles, and then new discoveries came, and so the scientists said that even molecules are made up of some other smallest particles called atoms. Atoms together, they combine together to form the molecule. Molecules combine together to form the particle, crystal and all, and when particles combine together, we get the material. So in this way, you can have the smallest building blocks. But when it came to the question of atom, what does atom contain? That was the question. And J.J. Thomson gave an idea that there should be some particles inside it, and we name them as electrons, and he named electrons are the particles which have negative charge in a cathode ray. And when a beam of electrons come from, when a beam of particles come out of a heated cathode, he named it as a beam of electrons. Electrons are negatively charged, and he gave a structure for the atom. And one conclusion was common with all the scientists and all the people, that is, atom must be neutral, because there is no attraction between material and material. There is no repulsion between material and material. So all the materials are neutral, right? No attraction between duster and chalk, no repulsion between chalk and chalk, nothing. So there should be a neutral material inside, and J.J. Thomson was the first person who gave an idea for an atom. Of course, his idea was found to be wrong later on, and it was disproved by his own student Rutherford. So what did J.J. Thomson say? J.J. Thomson said that atom is neutral, okay, but it is made up of charged particles. They have basic property called charge, and the whole atom is like he named it as plum pudding model. Plum pudding is a fruit. It is like a fruit. How do you see a fruit? For example, if you see some fruits, it contains many seeds inside, right? Some fruits have only one seed, some fruits have many seeds. So in plum pudding model, it is taken as a fruit and with so many seeds inside. So that was the idea of J.J. Thomson. But he didn't give any experimental proof to say it, but he just imagined that it is like a fruit. Fruit itself is positively charged. Fruit itself is positively charged. So for example, if you have a ball, solid ball, which is not hollow inside, say a spear, that spear itself is positively charged. But atom is neutral, sir. And there are electrons in the form of seeds, right, embedded here and there. And they are here and there located, very small electrons. And total charge of the electrons is equal to, so they are negatively charged. But total charge of the electrons is equal to the positive charge of the atom. That is a fruit. Suppose there are say 10 10 seeds, say 10 electrons. That is only a model. 10 electrons inside the fruit, 10 electrons inside the atom. Each electron is having a charge of say -2 coulomb. -2 coulomb, -2 coulomb, -2 coulomb. Like this, there are 10 electrons. So what is the total charge? -20 coulomb, right? Then the charge of the fruit itself is +20 coulomb. Like this. So fruit itself is positively charged. By the same amount, all the electrons collectively produce negative charge. What is the total charge within this system now? If you call this as an atom, the total charge is neutral, because -20 coulomb from 10 electrons totally makes -2 coulomb from each electron by 10 such electrons makes -20 coulombs, and +20 coulomb is the charge of the whole fruit. So totally it is zero, neutral. That was the idea given by J.J. Thomson. So this is called Thomson's model of the atom. Until that, nucleus word was not coined. Nobody used nucleus word, because the people had no idea of the structure of the atom, very similar to the structure of the solar system. And the first person to think about this was Rutherford and his students, his followers, assistants, Giger and Marsden. They did one experiment. They had a doubt that the distribution may not be like this. The fruit may not have any charge. Of course, the positive charge is not distributed like this. And there was a historic experiment and which disproved Thomson's model. And Rutherford was able to say that his teacher's model, Thomson's model itself is wrong, and it cannot be so. And he gave a new model called planetary model, which says that nowadays we know it. It says that the whole positive charge is not distributed throughout like a fruit, and the electrons are not like seeds inside. Of course, he agrees that there are negatively charged particles called electrons, and that was given by Thomson, right? And there are electrons, but they are not distributed or stationary everywhere like the seeds in a fruit. He says the whole fruit, you squeeze the whole fruit into a small point one. The whole mass you take it, but don't distribute it throughout the fruit. You just squeeze the whole fruit into a small point mass and distribute the seeds here and there. That means the whole atom, in the whole atom, the total mass is concentrated at the central part called nucleus. The whole atom, the mass of the total atom, almost all the mass of the atom is concentrated at the central part called nucleus. Where are electrons then? Electrons are outside revolving around. Very similar to the solar system. You see, in the solar system, if you take the mass of planets, mass of all the asteroids, and mass of all the comets and everything in the solar system, in our solar system, put it in a weighing pan, right? Say there is a weighing balance, right? We will assume it. And all the planets, asteroids and their satellites, everything, put it in a pan of a weighing balance. Put sun in the other pan. You will find that sun weighs much more than all these children planets, children satellites and all the asteroids. Why it is? Because more than 90% of the mass of the solar system is the mass of the sun. Because sun has to, everything is revolving around the sun, and if everything is revolving around the sun, everything is controlled by the gravitational force. How should be sun? Suppose your sister, when you are a small kid, right? When you are a small kid and your brothers and sisters are also small kids and of different age, say 1 year difference like that. All of you, your brother, your sister and everybody, if you hold your father's hand and if you try to go around like this, if your father is not moving from his position, means how heavy he should be, isn't it? You are all kids. You pull his hands, another one pulls his another hand, and another child comes and pulls his shirt, but he is steady, he is not moving, means he should be much heavier than all the kids. Otherwise, all the kids will push him and they will take him away. So, the same thing happens in the case of solar system. Sun should be very heavy, and all the planets revolving around the sun should be, their total mass should be much lesser than the mass of the sun, so that the whole solar system should be balanced, right? You might have seen that hammer throw. In a hammer throw, we have a spear and we have a chain for it, and that will be rotated around the person's athlete or the sports person, and you will be rotating it like this and you will be throwing it away. So here is a chain and here is a spear with a hook, and here is a handle for it, and he will be taking it and rotating it and rotating it and rotating it and throwing it away. One who throws it to a farthest distance will be the first. In that hammer throw, you look into the person who is participating in hammer throw competition. They will be well built, their body will be very heavy. So they are not supposed to have a lean body like Usain Bolt, who is an athlete participating in 100-meter competition. No, here they will be heavy, well built, and they are trying to increase their mass, because with their heavy mass, if they turn that hammer, and they will be steady, and hammer will not be making them to rotate. Otherwise it will happen so, right? If you are a very lean person and taking a very large hammer and trying to rotate it with the difficulty, and once the hammer rotates the first round, in the second round you will be rotating around the hammer, you will be thrown away. So you should be built very heavy. So 90% of the mass of the solar system is in the sun. Remaining 10% is in the other parts of the solar system. Similarly, Rutherford came to the conclusion that the 90% of the mass of the atom should be concentrated at a single point, and that is called nucleus, and he is the first person who coined the word nucleus, and the nucleus word is given, and that is the central part of the atom where 90% of the mass is concentrated, and remaining these children electrons with lesser mass are revolving around the nucleus. There are electrons, but they are not embedded here and there like seeds. They are rotating around the nucleus in the circular path. That is what Rutherford said. They are the circular paths where they can revolve around. Is there any rule that electrons must revolve around in a particular orbit? Rutherford said, no, not like that. Whenever electron gets some energy, it can go to the larger path. Whenever it gets lesser energy, it can go to the inner path. So it can be revolving around anywhere. As if you rotate a stone using a string. What should be the length of the string? You can take any length of the string and you can rotate it, no problem. But here it is not so actually, but later on Rutherford's model couldn't explain some of the things, but still it gave a very good foundation for the structure of an atom. Now, how could Rutherford come to the conclusion that there should be a central part and you have to squeeze all the atom into a small part called nucleus and then make the electrons revolve around the nucleus? Why this conclusion was made? And it is because of a very historic experiment, that is Rutherford's alpha particle scattering model, right? By then, when Rutherford had this idea, radioactivity was discovered. And when a material emits alpha, beta, gamma, when a material undergoes disintegration, that means deteriorating, its atomic number and mass number are decreasing with time. Once the radioactivity starts, of course, we will study that later, once the radioactivity starts in a material, it starts losing its basic particles, and its atomic number and mass number goes on changing. And such material, when it is taken and observed, it is found that some heavy particles are coming out of that radioactive material, and they named it as alpha particle. And such alpha particles were taken from the bismuth. Bismuth is a radioactive material. From the bismuth, radioactive materials are alpha particles are radioactive radiation, not radiation. Radioactive particles like alpha particles were taken, and they were made to hit on the target. And we will see the experiment. So the 3 persons worked under this experiment. One is main J.J. Thomson, not J.J. Thomson, Rutherford, his student, right? J.J. Thomson's student, Rutherford. And Rutherford's student is Chadwick, right? And they are the 3 people, one student of the other. So Rutherford, okay, James Chadwick, his student, and Thomson, his teacher, right? Okay, we will see that. Rutherford and Geiger and Marsden. Three people. This the credit of this experiment goes to these 3 people. And final conclusion was given by Rutherford after observing all the experimental facts. Now, what did they do? They took bismuth, right, as a source of radioactive material, because if you take bismuth, you will have plenty of alpha particles coming out of it. And these alpha particles, of course, they are highly energetic particles, and they are harmful to the, if you get exposed to alpha particles, it is little harmful. So, and these alpha particles and of course gamma radiations are very harmful. So this radioactive material must be always taken within a blocking material like a lead block. Lead block blocks some of the radiations, harmful radiations from the radioactive material. So you have to block it first. Only in a particular direction the required radiation has to be allowed to come out, otherwise it is very hazardous. Always radioactive materials, we hate these nuclear weapons. Why? Of course, in the olden days people used to fight with the sword, arrow and all, right? Nowadays we have nuclear weapons, but people hate nuclear weapons. Why? Because once the nuclear explosion occurs, large amount of heat energy, sound energy, light energy, kinetic energy of these small particles, everything will be released, and they destroy everything. Okay, whatever is destroyed, gone. But whatever the remainings of the nuclear bomb or nuclear weapon is available in the space, that place where it is blasted, they are very, very hazardous. They keep on emitting hazardous radiations like alpha, beta, gamma radiations. And these gamma radiations are very harmful, even beta radiations are also harmful. And if after the explosion also for many years, if the people go there, they will be exposed to the gamma radiations, and that creates lot of problems in their health, and it creates or it produces lots of diseases, and that is also dangerous. Okay, second impact. Third impact, suppose a person gets cancer or something from gamma radiations, or if some property of his nucleus is changed or cells are changed, and that genetic change will be brought to his children. It will be carried throughout his offsprings. So it is not only harmful at that moment, it is harmful in the later stages also, it is harmful in the next generation also. That's why we hate it. So the radioactive material must be taken in a particular chamber, and only harmful radiations must be blocked. Okay, we will take bismuth and we will keep it in front of lead blocks. Why lead blocks, sir? Lead blocks, they are very heavy and they block all the radiations going in all the directions. It allows the radiations going only in particular direction. So make a hole in the lead block. So this is the lead block. Okay, let the alpha particles move like this. So here is the source, that is bismuth. and let they fall on a gold sheet. Gold is highly malleable. Suppose you want a very, very thin sheet, better you prefer gold. Why? Gold can be made into very thin sheet, but still it is stronger. It is malleable. Even if you bend it, it doesn't break. So here is a gold sheet, and it is made to fall on the gold sheet. Yes. This is very, very important experiment. As far as exam is concerned, its conclusions are important. Okay. This is the gold sheet. So I'll name it gold sheet. How much thick? 10 to the power minus 6 meter thick, say. Micrometer. Very, very thin. 1 micrometer thick. Okay, these alpha particles are made to fall on, and so only the alpha particles moving like this, gamma radiations are like this are blocked, right? Alpha particles moving like this, only through this hole of the lead blocks will pass through, and it is made to hit the gold foil. Still, it is not symmetrical, right? So I have to put it here. Yeah, this is gold sheet, which is 10 to the power minus 6 meter thick. Now, what happens to these alpha particles emitted from the bismuth once they hit the gold sheet? Some of the alpha particles passed through the gold sheet. Most of them passed through the gold sheet. Very few of them returned back. Right? They went to the gold sheet and returned back, and they were detected using a detector. Some of them just deflected by an angle. I will call it as scattering. Scattered by an angle and went away. Some of them scattered by more angle went away. Some returned back, some went straight. So they were detected. How many went straight, how many returned back, and how many went through an angle? These are all detected using a detector here. And there is a curved concave shaped detector or a receiver, and it is coated with zinc sulfide. Why it is zinc sulfide? Because these alpha particles moving, and again the same barter system, right? When the alpha particles move with high kinetic energy and they go and hit the zinc sulfide, the alpha particles lose their energy, and the zinc sulfide electrons absorb that energy. So exchange started. Alpha particles gave kinetic energy to the electrons, electrons received that kinetic energy, and they returned back that energy again in the form of light. So flashes of light are observed on this zinc sulfide coating, which is given here, right? So this is coated with zinc sulfide like this. Okay, zinc sulfide, and we choose zinc sulfide because we will get the energy in the form of light very easily. It is very quick, it will give the response very quickly. Okay, now there is a detector here. So a detector is made to move to see a microscope. Actually, detector means microscope, which observes the flashes of light formed on this zinc sulfide screen. So this is zinc sulfide screen, right? So the alpha particles moving straight, alpha particles moving like this, like this, like this, they were all observed by observing the light flash on this screen, right? And this is the detector microscope, which can see the flashes of light. So that is a beautiful experiment. Now, what observations they recorded in this experiment? They did this experiment, and alpha particles were made to move on the gold foil, and the detector is made to move throughout the screen, and the direct moving alpha particles moving here with the lesser angle, more angle like this. Depending on the flash of light observed in these paths, they were able to detect how many alpha particles went back like this. Some of the alpha particles went back. How many alpha particles they went with some angle like this, more angle like this, and a graph was drawn. That was the first conclusion. They made some observations here. How many number of alpha particles are received? That depends on how much amount of flash of light is observed in the microscope. If you observe more flash of light here, it does mean that many alpha particles are received in this position. So number of alpha particles received versus angle of scattering. See, some experiment, how do they change the approach of the physics itself, approach of the science itself? Thomson gave a plum pudding medal, right, which says that the whole atom is positive, if the whole ball is positive, within that there are electrons like seeds. But this gives a entire different idea. When this graph was drawn, the nature of the graph was found to be like this. What do you mean by that? For smaller angles of scattering, that means the alpha particles which move almost like this, like this, like this, like this. For small angles of scattering, if you come here, the number of alpha particles is much more. Is it not so? For example, if I 0 degree, 10 degree, 20, 30, 40, 50, 60, 70, 80, 90 like this if I draw. For 10 degree angle of scattering, that alpha particle which went like this and bent very little, that alpha particle which went like this and bent very little, or the alpha particle which has bent very much more, some alpha particles going like this, some alpha particles returning back, more angle, 180 degree, returning back means 180 degree. If you search for less angles, you will find that the number of alpha particles is more. If you search for more angle, you will find that the number of alpha particles is less, correct? Can you study that? Suppose you go for 90, 100, 100 and 180 like this, number of alpha particles will become lesser and lesser. Alpha particles scattered at a lesser angle are found, number of alpha particles scattered at lesser angle are found to be more. Alpha particles scattered at more angles is found to be very less. That means more alpha particles are found to be scattered at lesser angles. And it is found that 1 in 8,000 alpha particles, 1 in 8,000 almost. That means if you take 8,000 alpha particles, among them only one was found to be returning back like this. Scattered at very large angle, 180 degree. That alpha particle going like this and coming back like this. 1 in 8,000 alpha particles were found to be scattered at how much angle? 180 degrees. Very less. So from this, Rutherford was able to conclude that Thomson's model is completely wrong. Why? I'll give an example. Imagine that you are put in a dark room, right? You can't see anything, right? And you can't go beyond a certain stage. It is like a classroom, say. It is dark room and nothing can be seen. You are given so many balls, colored balls, balls with which are immersed in paint, right? If you throw it to the wall, you can have a mark on the wall, right? Imagine that there is a spear suspended at the in front of the blackboard or whiteboard. We will say it is a whiteboard. A ball is suspended on the in front of the whiteboard. You can't see that ball at all. It's a heavy spear, say. So here is the whiteboard and here is the heavy spear and you are standing here and you can't go beyond this, right? Okay. This is a very heavy sphere suspended and this is it is very dark and here are balls with you which are immersed in color, say white color. In white paint the balls are immersed and the heavy sphere is suspended. Next day morning, of course, you will get light and now it is totally dark. It is 12 o'clock night and there is nothing, no power. Tomorrow morning you have to, and tomorrow morning somebody will come and take away this sphere, right? Before you get up, somebody will take the spear. So you may not be able to see the spear. But tomorrow morning you have to say that whether the spear was smaller, whether the spear was larger, and whether the spear was having so much of radius and all. But you are given balls. What you can do? At night, in the darkness, simply throw away the balls. Throw away the balls. When the balls are thrown away, you can see this, I think, right? If you can't see this, you can't do this experiment at all. Yes, you can see this. Simply start throwing the balls towards the whiteboard. Keep on throwing. Imagine that you are given so many number of balls. Throw balls on all the directions and tomorrow morning get up. You don't see the spear at all, but you can have the whiteboard, right? On the whiteboard, if you have thrown a ball directly like this, there is no mark in this region. And all the other points will have marks where there is no board, right? Where there is no spear. Suppose the spear is kept here. When you throw the ball from other side and when it hits the spear, it returns back. And if one ball, colored ball or ball immersed in paint, if it hits the spear by the side, it goes and makes a mark on the whiteboard here. and all the balls which are thrown in the outside the region of the sphere, they make the mark on the whiteboard, and that part of the sphere in front of this will not have any mark. So you have numerous balls. In the night you have thrown all the balls towards the sphere, and next day morning you get up and see the whiteboard. Wherever you have marks, definitely in the directly opposite to that positions where you have marks, there is no sphere, and wherever you don't have mark, definitely directly opposite to this, there was a sphere. There was a sphere. So measure that area where there is no mark and measure the radius. You can find out. You can just by up to some extent, up to some approximation, up to some accuracy, you can find out the size of the ball. If I do the same experiment tomorrow, you are given with so many number of balls, you are put in the dark room, board is ready, whiteboard is ready, clear board, and you are given with so many balls. Again you throw the balls. Next day morning you find that large region in the board is clear without any mark of the thrown balls. That means that was the largest sphere. Similarly, we are in darkness. We don't know how the atom is, right? So Rutherford is totally in a darkness because he is not knowing how the atom is. Thomson says that it is like a fruit, but we don't have any clear idea. There is no experimental proof. This is what is done by Rutherford. He simply started throwing alpha particles towards the atom. It is found that very few alpha particles return back. So particles scattered at the larger angles, their number is very less. What do you mean by that? Very simple. If an alpha particle is directly going towards the nucleus or atom, it should be returned back, right? That means if the size of the atom was larger, most of the alpha particles might have returned back, isn't it? Since very few alpha particles were returning back, it is not the atom is not so much larger. And he thought of it like this: atom may be larger because size of the atom was given in kinetic theory of gases. It was about 10 to the power minus 10 meters, 10 to the power minus 11 meters, like this. The size of the atom is larger. That means in the atom, he concluded that most of the space must be empty, as if in the solar system. Our solar system is so large, it starts from Sun, it goes up to Neptune, Pluto, and even after that some asteroids or something, right? It's a very huge solar system. But remember that most of the space in the solar system is empty, isn't it? In the same way, since only few alpha particles return back, in the atom, almost most of the mass must be concentrated at a smallest part, and that part is named as nucleus. That is how he concluded. Since most of the alpha particles didn't return back, only very few alpha particles returned back. In a nucleus, even though the size of the nucleus is 10 to the power minus 10 meter, there should be a very, very small sized, the whole mass concentrated place, and he called that place as the nucleus. So that was the first conclusion made. In an atom, almost all the mass is concentrated in a central part called nucleus. It is as if you have a heavy marble, you just paste some cotton around the marble like this. If you have a marble, where do I write it? If you have a heavy marble like this, marble is heavy, and you just paste some cotton around it like this. Now the whole structure looks very larger, but where is the mass? Mass is concentrated at the center. Marble is very heavy. What about cotton? Cotton is very lighter, right? The whole system appears to be larger, but whole mass is concentrated at the center. So in an atom, almost all the mass is concentrated in the central part called nucleus. And where may be the electrons? Electrons may be revolving around the nucleus in definite orbits. And how do they revolve around? What is the centripetal force? And all those answers were given by Rutherford later. But we will concentrate on this experiment itself. One more conclusion was made by, of course this is not over, I will have to talk more about this in the next class also. This is just an introduction for the experiment. Okay. Giger, Marsden and Rutherford. Of course I have to draw that graph again. Now they defined one term called impact parameter. What do you mean by impact parameter? Again another diagram was drawn where, of course, shall I rub this? Here is bismuth and this is alpha particle, okay, like this. Now, suppose this is the target nucleus here. So I will finish how the experiment was made. Conclusions we will do it in the next class. Now again another thing, why gold is chosen? One is gold can be made into any thin sheet and it is highly malleable. Malleable means the thinner you make, still it is stronger and it can be bent, it doesn't break. It doesn't break. Another thing is gold nucleus is heavy. Its mass number, atomic number is 79, right? 79. Gold is heavy. And whereas the hitting alpha particle, its atomic number is 2. Gold is 79. Now, when you, I already have told, you are the hammer thrower, right? You should be heavy. You shouldn't move. And hammer should not be there and you should be on the, if the hammer is there only and you are in the certain distance, you will not be given the prize, right? So, you should throw the hammer, you should be heavy. So, in the same way, gold should be steady. It shouldn't move. Alpha particle is the experimental particle. We have to study alpha particle, how it is moving, right? So, alpha particle must be lighter and gold is heavy. That is why gold is chosen. Gold atom is very strong and it is very heavy. So, it doesn't move at all, and alpha particle is very lighter compared to that. So, it gets scattered when it reaches a gold atom. Okay, now what is impact parameter? Suppose this is the target nucleus. Which is the target nucleus? Target nucleus is this gold, and here is alpha particle. The alpha particle which is moving directly towards the gold like this, return back, correct? Because its initial velocity is in this direction. Suppose we are making many alpha particles to move on to the target. It is not a single alpha particle. When many alpha particles were made to hit on that, some of the alpha particles may be going directly into it, and some of the alpha particles may be going like this. What will happen to this alpha particle? It moved like this, right? It was repelled by this target nucleus somewhat like this. What about another alpha particle which is moving little bit far away? It went like this and it experienced less bending because it is far away from the target nucleus, right? And the balls which you throw, which hit the side of the sphere, they deviate like this. The ball which hits to the center of the sphere returns back, and the ball which doesn't touch the sphere goes straight, right? If another alpha particle is chosen far away, it almost went straight without any bending at all. So most of the alpha particles went straight without any scattering, because they didn't get any force from the target atom at all. They are very far away from the target atom. If they are very far away from the target atom, means that target atom should be very small, right? Its nucleus should be very small. If that was a larger one, if a whole positive charge was distributed in the atom itself according to J.J. Thomson, then what would have happened? Many alpha particles must have experienced force. Here only very few alpha particles returned back. Some of the alpha particles went through large angles and some of the alpha particles went through smaller angles. Some of them didn't deviate at all. And this angle, you see, theta, here theta is 0. Here theta is 180 degree. They define a word called impact parameter. What do you mean by impact parameter? See the original direction of velocity of the alpha particle and find out the perpendicular distance from the original velocity vector to the target nucleus. Original velocity vector is this one, right? This is the original velocity direction. Of course, then later on it changed, and this is impact parameter. I call it as B. Impact parameter B is the perpendicular distance between, impact parameter B is the perpendicular distance between the initial velocity vector and the target nucleus. Not this distance, not the distance from here to here. Initial velocity vector is directed like this. Its perpendicular distance towards the target nucleus or target atom. That is called impact parameter. Now, for this one, impact parameter is 0. isn't it? Because that alpha particle is along the direction of the target nucleus. So if you try to get the perpendicular distance of the velocity vector and the target nucleus, you get answer 0. There is no perpendicular distance at all, because the velocity vector itself is along the target nucleus. So if the impact parameter is 0, deflection is very high, 180 degree. If the impact parameter is more and more, deflection will be lesser and lesser. Here you see, the impact parameter is more. Impact parameter is more. The perpendicular distance between the initial velocity and the target nucleus more. More the impact parameter, lesser will be the deflection of the alpha particle, and lesser the impact parameter, more will be the deflection. For impact parameter 0, the deflection was found to be 180 degree, and so these conclusions were made, and they were observed in the experiment. And what conclusions they draw in the whole experiment, we will see it in the next class, because my time is over, and my camera is getting ready for the second file, then it becomes a problem. Okay, we will continue it in the next class. Till then, I will send you the notes, and keep reading the notes. Of course, many of the things you can follow it from the notes itself here, but you can watch my video for minute things. We will meet in the next class. Thanks for watching my video.